Hello and welcome back. In section 5.6, we get to work on logarithmic and exponential equations. So we'll start with one that's going to show off sort of an interesting property of these. So we'll do 2 times log base 7 of x is worth the log base 7 of 16. Now first of all, I can turn this into the log base 7 of x squared using the properties we've done previously in the section. That's equal to log base 7 of 16. And as long as my bases match, my arguments have to also match. So then x squared must equal 16, so x squared minus 16 is 0. So x plus 4 by x minus 4 is 0. So x is plus or minus 4. Now here's where things are a little different though. Recall that the domain for a logarithm was the set of all positive real numbers. Negative 4 does not qualify. So our solution set will only contain the positive 4. We have an excluded value in our list of possible solutions. This next one, again, we get to do a little bit more practice with the properties from previous sections. So I have a pair of logarithms, but lucky us, they happen to have the same base. So the log of a sum will turn into the log of a product. So log base 2 of the product, x plus 6 by x plus 7, is now worth 1. So I kept the common base and turned it into a product. So the sum of logs turns into the log of a product. Now at this point, my variables are trapped in the argument of the logarithm. I can go back to exponential notation to fix that. So the base stays your base. The other two things trade sides. So 2 to the first power is worth x plus 6 by x plus 7. So then 2 is worth x squared plus 13x plus 42. So 0 is worth x squared plus 13x plus 40. That is factorable over the integers. So let's see, we've got a plus 5 and a plus 8 will do both jobs nicely. So x equals negative 5 or x equals negative 8. Again, I want to check for any domain issues. So negative 5 plus 6 is 1. Negative 5 plus 7 is 2. Those two are acceptable in the domain. Negative 8 plus 6 is negative 2. Right away, that gets thrown out. I only get to keep the negative 5. Okay, so the next one, I'd like you to sort of pause it once I've got the problem all written out and give it a spin on your own. Okay, go ahead and pause that, see if you can solve that. Okay, welcome back. So left-hand side, we have the same base, the unwritten e. So then this is the natural log of the quantity x by x plus 6. It's worth natural log of 2x plus 45. So now I have a single log on both sides with the same base. The arguments are going to have to be equal to one another. So x squared plus 6x is worth 2x plus 45. It's an ugly 45 there. So x squared plus 4x minus 45 is worth 0. So this is also factorable over the integers. X plus 9 by x minus 5 is worth 0. So x is negative 9 or x is positive 5. Right away, the negative 9 gets tossed. We have an x by itself there, so x can't be the negative 9. Natural log of 5 is a real number, natural log of 11 is a real number, and natural log of 55, 10, and 45 is a real number. So this one we get to keep. The negative 9 we don't get to keep. Alright, so we looked at a few where we started with logs. Now we'll look at a few where we start with exponential form. So I have 3 to the n is worth 20. If my variable is in the exponent, I can use logarithms to get that out of there. So we can take the natural log of both sides. So natural log of 3 to the n is natural log of 20. Exponent turns into a factor, so n natural log of 3 is worth natural log of 20. Divide both sides by natural log of 3. So n is natural log of 20 divided by natural log of 3. Notice that is not the same as natural log of 20 over 3. That will give you a completely different value. Check it out on your calculator if you need to be convinced of that fact. And again, like before, I did have the warning in another section. If you get numbers like natural log of 12 divided by natural log of, let's say, 3, we cannot turn that into natural log of 4. We can't do any reducing with arguments. Alright, so next one we'll look at 7 times 5 to the x is worth 17. This one I don't have just a base to a power with its own side of the equal sign, so I'll fix that first. So 5 to the x is worth 17 sevenths. Now I can do my usual, I'll take the natural log of both sides. So x times natural log of 5 is worth natural log of 17 minus natural log of 7. So log of a quotient turns into a difference. So then we just divide both sides by natural log of 5. So x is natural log 17 minus natural log of 7 all over natural log of 5. Now, we don't necessarily have to use the natural log each time. We could use really any base that we wanted. We could use just arbitrary base b. We could have used base 10. And then these would be LOG, LOG, and LOG. They will have the same value as the natural log had. Alright, let's see. So our next one, do 7 to the 2x minus 1 is worth 2 to the 3x minus 5 power. So again, my variables are trapped in the exponents. I don't have any coefficients on either side, so I'll just jump right in with the natural log of both sides. So natural log of 7 to the 2x minus 1 is worth natural log of 2 to the 3x minus 5 power. Exponents turn into factors. These exponents happen to have multiple terms, so they need parentheses when they become factors. So a little bit of distributive property, and we have turned this into a linear equation. The numbers, granted, are not super pretty, but they are just linear at this point. So I have 2x natural log 7 minus natural log 7 is worth 3x natural log 2 minus 5 natural log of 2. From this point, everything with an x is going to go to one side, everything without goes to the other. So 2x natural log 7 minus 3x natural log of 2 is worth negative 5 natural log of 2 plus the natural log of 7. Left-hand side, I can factor in x. So I have x by 2 natural log 7 minus 3 natural log 2 is worth natural log 7 minus 5 natural log 2. So then I just find the quotient of that, and that's my solution. So x is natural log 7 minus 5 natural log of 2 over 2 natural log 7 minus 3 natural log of 2. And of course, I can't factor either the top or the bottom other than a trivial 1, so there's no reducing that can be done with this one. And occasionally we get one that is sort of a hidden quadratic. So 25 is the same as 5 squared. So I have 5 squared to the x minus 5 to the first to the x minus 72 is equal to 0. Now, power to a power, our shortcut is to multiply the exponents. Multiplication is commutative, so I can also call this 5 to the x squared minus 5 to the x. 5 to the x to the first minus 72 is equal to 0. So we're going to let u equal 5 to the x, which means then I have a u squared minus u minus 72 equals 0. That one we can just factor over the integers. So u equals 9 or u equals negative 8. Then we put the original back in. 5 to the x is 9, or 5 to the x equals negative 8. Positive number to a power is never going to give me a negative. I can discard that solution. So now I'll just take the natural log of both sides. Natural log of 5 to the x is natural log of 9. X natural log of 5 is worth natural log of 9. So x is natural log of 9 over natural log of 5. And that's as far as we take that one. And again, this isn't the only representation of the solution. You might see log of 9 over log of 5. You may even see it just written with a base 5 as log base 5 of 9. All three of those are equivalent. All three of those are exactly the same value. So then one last little trick they have us if we have one where we just need to estimate. So some of these things we would need calculus or numerical methods that we haven't learned yet. So if we get something like x plus 2 to the x is worth 7, and they ask you to approximate the solution, in y1 you're going to have x plus 2 to the x, in y2 you're going to have a 7, and you're going to look for the pointer points where those two graphs intersect one another. So clear out any older functions that you've got. Try to find that sweet spot again where I have visible graph, but not much in the way of glare. So if x plus 2 raised to the x, and our other is 7, we'll start on zoom 6 and adjust if we need to. And it looks like our solution is nicely on screen. So second and calculate, we want where they intersect. First curve defaults to y1, second curve defaults to y2, and then we arrow, in this case to the right, right or left until we're very close. It'll ask for a guess. It'll think for a minute. It's going to give me two numbers. Remember, the original was in terms just of x, so I'm not that interested in the y value. In fact, that is not part of my solution. So x is approximately 2 and 248 thousandths. I would not put an ordered pair for this since we did not have a y in the original. We put the y in as sort of a placeholder. All right, so in 5-6, I would recommend 5 to 93 on the odds, 105 and 107, and I'll try to come up with a rough equivalent for the MyMathLab fans. If you have any questions, please get in touch with me. Otherwise, I will see you next time.